our next topic. And we're talking about machine intelligence here. Now, I don't know if you've ever been on Yahoo Answers, for example, right? I just read something of a person who was looking for the answer to 100 minus 90. And the thing was, somebody answered on Yahoo Answers saying, well, you're an idiot, why don't you just Google it, okay? Now, what I'm trying to say is we could argue that humans are getting or are becoming stupider, or at least lazier on the one side, but there's no doubt that machines on the other side are becoming more intelligent. And this is exactly what we're going to talk about now, artificial intelligence and how it holds the promise to revolutionize industrial applications. And this revolution will take place in two major dimensions. That means intelligence and autonomy. Please welcome our expert in the field. Here is Dr. Michael May. Welcome.
Hi.
Great to have you with us.
Okay, so I will be talking today about machine intelligence and the advent of artificial intelligence in industry. You saw today a lot about MindSphere probably on the MindSphere booth, so you saw how you can connect devices to the cloud and then analyze the data from a factory or from a plant using condition monitoring. And Industry 4.0 is fueled by data, and MindSphere is providing this fuel. But is this the end of digitalization? No, it's not. So in my opinion, it's just the beginning of a much larger disruption which is just around the corner, and this disruption is artificial intelligence. And I will show you some examples of how we approach this at Siemens. Now, artificial intelligence, it's a big topic in the news, and there have been some really surprising breakthroughs in this technology in the last couple of years. So if you think about IBM Watson winning a game, a quiz show, Jeopardy, against the best experts in the field using question answering technology, or if you think about Amazon's Alexa, which is now coming into the consumer market and helping you to translate speech into questions and into answers, into actions done by Alexa if you want to order something or listen to music. Or think about DeepMind's AlphaGo program that won a match against the Go world champion. Very surprising for everyone. Everybody thought that's at least 10 years away, if not more. So a lot of things happened, and much of this is fueled by a technology called deep learning, which is the modern form of neural network technology. So complex technology which mimics a little bit how the human brain works and comes up with learning from lots of data. And all these advances, they have been made possible by advances on the algorithm side, so that's the deep learning, by having more data at our disposal. Think about image data in the internet, where previously you had just very small amounts. Now there are millions of images from which you can learn. And of course the computing power you need to digest this data and to learn from it. And so also, if we look at the industrial area, the AI revolution will take place along two dimensions. The first one is intelligence, the second one is autonomy. If we look at the first dimension, intelligence, that's an area where Siemens has a lot of experience already. More than 20 years, rather 30 years of experience in making the Siemens products more intelligent. For example, if you take steel plants, already 20 years ago, we deployed the first neural networks in steel plants for monitoring and improving the quality of the process. So that was rolled out back in 1995 in more than 30 plants. So intelligence is a topic for Siemens for a long time. Or take another example, calculating the remaining useful life for gas turbine. Or yet another example, doing root cause analysis in the CERN Hadron Collider. So it's a large installation of Siemens Simatic, and to doing root cause analysis to prevent failures and to maximize uptime is very important for that. So intelligence, we are already in a good shape, but now the next level of innovation comes, and this is improving control using deep learning and so-called reinforcement learning. And this is a topic where we have been working on for roughly 10 years. So it started 10 years ago, actually with a mathematical proof that any dynamical system can be modeled arbitrarily well using so-called deep recurrent neural networks. And so we knew it's a very powerful technology because basically everything Siemens is doing can be seen as a kind of dynamical system, so that shows behavior over time. And then the next step, we build out of this a quite comprehensive technology, have a quite number of patents on that. So we learn to apply deep neural networks for modeling the behavior of a dynamical systems, and we started to learn how to control the behavior, to learn from past behavior and to come up with an improved control strategy on that. We started with very simple examples like balancing a flag ball on a cart so that it does not fall aside. And then after time we went to more complex equipment, especially turbines, wind turbines and gas turbines. And now we are in a position that these technology become productive in the field. So from research, which took about 10 years, now to productive. And this topic is called self-optimizing turbines using reinforcement learning. And how does this work? So actually it works that you first learn from the past behavior of the machine. So you have a lot of sensors, hundreds of sensors that give you data how the machine works under different actions that you apply to the control parameters. And you learn using deep learning how to simulate the behavior. So give this or that action to the parameters, how does the system state behave. And if you do that well, and you see an example here in the picture, you have a quite good simulation of the behavior. And if you did it really well, then you can start to answer what-if questions. So what would happen if I put the parameter in a position that have not been tried before? And then you get a simulation of that behavior that's showing in the green curve. So it shows a behavior which has not been observed. And if you have figured out how to do that, then actually you can start to learn completely new behavior in a simulated environment. And that means you can extend the classical control loop of a gas turbine using artificial intelligence. So on the left side, you see a classical control loop where you get information about the state of the system, and then you apply actions according to some fixed and static control policy. So that's how it's done today. But with the help of machine learning, you can make this process dynamic, and you can make the machine learn from its past behavior. So you collect the data. For that you need, for example, MindSphere for collecting the data, storing them, using deep neural networks to learn how the machine behaves under different conditions. And then the machine starts by itself to figure out a different parameter setting, and it just observes in the simulated world what works good, what works not well. And for everything that works good, it gets a reward, a digital reward, or if it doesn't work out, it gets a punishment, a digital punishment. And this process is called reinforcement learning. And reinforcement learning and deep learning, it's also the technology Google has been using to win in the game of Go against the world champion. And so Gartner, as a analyst, they have been commenting on that. Great achievement, really great achievement, totally unexpected, but it remains to be seen how this translates from a game world into the real world. So where you have lots of security issues and lots of other issues with the physical real systems. And you might be surprised to hear that at Siemens we have already, and before Google won this game of Go against the champion, we have already translated that to the real world, and it's running in productive mode at some of our customer side. And so that is what I call lifelong learning for gas turbine. So implementing a control strategy, learning from the experience of one gas turbine or a full fleet of gas turbines, collecting the data, doing simulations inside the machine, coming up with better actions that improve the behavior of the machines, and then deploying that improved control strategy on the machine. And then doing that again and again from time to time, you get this lifelong learning. And so what I've shown here for the gas turbine is just one example. We have very similar examples for wind turbines, not yet in productive mode, but in extended field testing, and other applications at Siemens are underway. As I said, in the beginning there was a proof that any dynamical system can in principle be modeled this way, and since most of the things Siemens is producing are somehow dynamical system. This is a very general methodology to apply. It will not work in every case immediately, but over time, I'm pretty sure we will see more and more application where intelligence enters into the machine and helps to improve the control strategy. For Siemens, this has been based on a lot of research in the area neural networks and then reinforcement learning over the past decades, I should say. And we use our experience in the industrial environment, so the know-how of the experts, how to interpret the data, and then the know-how of the artificial intelligence to implement these kinds of systems. Gas turbines, wind turbines, smart grids, medical images. So examples are all around where you can use this kind of autonomous learnings. And our ambition of Siemens is in this area of applying artificial intelligence and machine intelligence to industrial application to lead the way in industry. Thank you very much for your attention.
Thank you also.